Hello, my name is Casper. I am from QuantStamp, and we are a security company. We do security audits for layer 1 blockchains. Now also we work with cross blockchain protocols with layer 2. And I'm going to present stuff that was worked on by my colleagues. So that's Martinet, Alex, and Martin. And this is a pretty hot topic right now, because this one is about bridges. And bridges are super relevant right now, especially in the context of layer 2. So why is this talk relevant? So perhaps you heard about some projects that got hacked, and maybe some funds that were at risk. So if you sum this up, I mean, just right here, we are talking about pretty significant amounts. So let's look at, what does a bridge do? So the role of a bridge is to move assets from one chain to another chain. But you don't really move the assets, because these are totally separate entities. So for example, if you deposit assets on ETH, and you want to move to a layer 2, so this is what happens. On Ethereum, you would have a custodian, which is a smart contract in which you lock some assets up. Then you have this communicator component, and it pings the contract on the other chain. And then the other contract on the other chain just means other token. And you can think of it as a dead token. And this is what actor on the other side receives. Now, when you want to withdraw funds on the chain where you deposited, first you burn the tokens on the chain where the dead token was issued. Then the custodian on the L1 gets pinged, and then your tokens are released. And this is how you can get them back. So far, regarding the structure, we've seen the asset custodian and the debt issuer, and both of them, they are smart contracts, but they live on different chains. And then we have the communicator, and communicator is an off-chain component, which really is an oracle that provides this communication that goes in both directions. Now, there are a bunch of attack surfaces, and the goal of this presentation is to demonstrate to you that there are a lot of things that can go wrong with bridges, and things can go wrong with the custodian, with the debt issuer, with the communicator, interfaces, and with the network itself. And we'll look at some of the attacks that already happened or will happen very soon. But most of them already happened, unfortunately. So first one is an example of an attack on a custodian. So here we had a cross-chain communicator contract that used to ping this asset custody. And within this asset custody contract, there was a list of privileged addresses that were able to release the funds on one end. You can also notice that this cross-chain communicator could call the function change custody address, because that's what the team wanted. So if you're an attacker, you may think, OK, how can I take advantage of this? So first, you can think, OK, I want to take control over the privileged addresses. And then I can change the list of the addresses that can release the funds. So whoever the attacker was, they noticed that the cross-chain communication contract was sending a signature to any contract. So you could specify which function you want to call and what the target is. Really? So that's pretty great, because there is this change custody address, and you can provide a signature of this function as an input to this cross-chain contract. And as a target, you can put the custody, and then you can just change the address of the list with privileged addresses. So that's exactly what they did, and they were able to release the funds. So it seems trivial, but in a complex system, it's not always that trivial to spot issues like that. Oh, and by the way, the names that I put on titles, these are my names. I thought that they just reflect the best what actually happened. I don't think that there is any standardized list of names for these attacks. Here we have another example. So this one is also pretty interesting. So we have both sides. We have a custodian and a dead issuer. And if you burn your dead tokens on one side, then you would receive here a proof that you burned these tokens. And then you would have to submit the proof to the custodian to get the tokens released on the other side. In this specific project, there was a problem that the proof could be manipulated because, let's say, typically you would like to hash all of the values, but maybe they didn't hash everything, so some part of the proof could be manipulated, and you would not verify that it was manipulated. So this way, you could reuse the same signature, the same proof to release the funds multiple times. So basically, you would repeat, and you would get more funds using the same proof of burn. Again, this was another issue that actually happened. Now we can look at the other side with the dead issuer. So here, the way it was working was that the dead issuer had a verifier contract. So it would verify whether you can get the dead tokens or not. And the goal of the attacker was to bypass the signature verification so that then you can mint any amount of tokens you want. So this is how it looked like. So the communicator would initiate this debt issuance on the target chain, and then that issuer would check, with the verification contract whether this can go through or not. But the problem was that the attacker was able to submit the address of the verification contract. So you can deploy your own verification contract that always returns true. And then you can just mint as much as you want. Again, that's another example from the real world. So we covered contracts on both sides. Now, there are a lot of things that can go with the communicator as well. And actually, probably this component tends to be more difficult to verify because this is an off-chain component, and off-chain components, they tend to be much bigger than whatever you put on-chain. Here it was all, so basically the attacker wanted to trick the communicator into forwarding invalid messages so that they could mint dead tokens. And you can think of this as pulling the data source of an oracle. So here is what happened. So in this setup, we had this custodian contract on one end, and there is the communicator that listens to events from the custodian. But there was a bug in the communicator itself because whenever there is an event issued within a transaction, it would only check whether the first event of a given kind comes from the authorized contract, but it would not check whether all other events there are from the same contract or from another authorized contract. So basically, you could deploy a malicious contract that would emit the same events as the legit custodian contract. And then the communicator would just issue a lot more dead tokens it would ping the other side to issue a lot more dead tokens than you would normally get from a single deposit. Here is another type of attack. So this one is on the interface. So it is not exactly bridge specific, but it is very relevant to bridges. So imagine that a user just gives an infinite approval to the bridge, and actually that happens quite often, that people do. People provide much more approval than actually is needed in one transaction. So if the bridge doesn't sanitize the input, and for example, like in this specific case, it would allow executing, any function call to any contract. And this is, so in this specific case, one could just call transfer from even multiple times so that the bridge could transfer tokens from the user to the attacker. One way to deal with this is to revoke approval. And so myself, I've been doing audits like, I don't know, like 5 years when it comes to crypto at least. And I think that I've seen like maybe like between 1 and 3 projects that would revoke approvals automatically for you. Most of the time, you just set the approval and it sits there. So, even if somebody is not malicious, there may be a bug in the contract. It doesn't have to be a bridge, but like even a DeFi contract, whatever. It may happen that you can still get your tokens transferred out just because you gave this unlimited approval. So one way to deal with this is to always revoke the approval once you're done with the transfer and with the transaction. So here is another attack which is pretty similar. This one is more maybe a bit more interesting because here we use the permit functionality, and permit would just get typically it gets a signature where you just allow to transfer tokens on your behalf, and you sign the message, gets submitted, and then the transfer gets executed. In this specific case, though, the problem was with tokens that do not support permit, but have a fallback function that would not fail. Because in this case, you would call permit, or the bridge would call permit to check whether the permission is valid before transferring tokens from the user. And when you call permit and permit is not there, then the fallback function gets executed, nothing gets reverted, and the bridge considers that as a successful permission, and then just executes transfer from, and then would transfer tokens from the user to the attacker. Again, like one way to deal with this is to take care of the approvals. Okay, so this is the last attack. So this is something that we were thinking about when we had our own research retreat last year. And we had a write-up about this specific attack, even like before Vitalik wrote about it. I think it was maybe in January. I think it was in January that he wrote. So this one is pretty interesting because you can launch a 51% attack and take advantage of it, of this attack. Of the bridges in the following way. So you start with a 51% attack on your L1. Blockchain, and then you deposit assets. So you deposit to the custodian, then you get some debt token on the other side, and then you withdraw tokens by submitting debt tokens on that other side, and your, let's say, original tokens, they get unlocked on the L1. But now, since you launched a 51% attack, you would be able to cancel the transaction that deposited assets to the custodian. But you may still get these tokens back. So if you think that this is unrealistic, actually it is realistic because at least according to Crypto 51, 1 hour of an attack is like up to $2 million right now, which is not that much considering what you have in the pools. And you don't even need the whole hour to execute this attack. I don't think that this one happened, but pretty sure it's going to happen sooner or later. It all depends on the incentives and how much liquidity you have in the pools. If your attack, if you can gain more than $2 million, that's already profitable to you, and somebody will do it. So So these were some examples of the attacks, and this is just a short summary to highlight some of the issues that can go wrong with bridges. And there are a lot of them, because bridges are pretty complex pieces of software, even though it's not necessarily about the number of lines of code, but about complexity, and that you are dealing with like at least two on-chain components and one off-chain component that has to communicate with them. So when it comes to the custodian, like incorrect asset amount can get released with respect to the burn tokens, and you can get assets released, although no token got burned on the other side. And you can also have problems with transaction replays. And replays can go on both sides. And recently, actually, I was reviewing one of the projects, and for example, they were not dealing with any nonsense. And like anybody, pretty much could submit a transaction and get it replayed, and they were able to issue more tokens than they were supposed to. The same pretty much goes for a debt issuer. It's just on the other side. A lot of stuff can go wrong with the communicator. So like some of the stuff that I discussed, but also there may be some DOS attacks going on the communicator. You may effectively just break the bridge by by attacking this communicator component, and then nobody can send tokens either way. It all depends on how that communicator is designed. The interface is also a very important group of attacks, because this is more about the assumptions that you, as a developer of a bridge, have on the tokens or maybe other contracts that you are using. So it's always very important to state these assumptions very, very clearly, so that you or the auditors can verify them and then see what can go wrong. And then, yeah, finally, there is this 51% network attack. And again, if it has not happened yet, it will happen sooner or later, because there is more and more liquidity just locked up in the bridges. And I believe, as we are moving from L1 to L2, probably bridges will be the most critical parts of the infrastructure, because they will be holding a majority of the liquidity, so that you can, for example, trade or do something on both chains. And here the problem is that all of this liquidity is effectively centralized in these bridges, or different liquidity pools that are really part of bridges. So thank you very much for the attention. I think that was a pretty quick presentation. We are hiring. Actually, we are hiring like crazy worldwide. We are looking for auditors or people who are interested in doing research on security. And we've been around 5 years. I think that probably slightly shorter than Open Zeppelin, or maybe about this time. And like personally, I think it is a very cool field to be in, because as an auditor, you learn about all of the cool and new projects way before anybody else. Because before people deploy their projects, they want to make sure that the security is in place. So yeah, there are a lot of things that are pretty cool about security, although maybe the topic does not sound that sexy. Yeah, so thank you very much. And of course, and if there are any questions, very happy to answer them. They already happened. Yes, yeah. All of these examples, yeah. So I don't remember names, and I definitely don't want to name the names here, like where it happened. But all of these attacks, besides the network attack, they were present in the code. So that I know for sure.
And then in the interface example, presumably the user is approving the contract to use the tokens, not the attacker's end.
Yes. So the thing is that the bridge gets the approval from the user, and then bridge can execute transfer from, right? Yeah, the bridge construct can execute transfer from, and if the attacker can put their address as a target of transfer from, then the attacker gets the tokens.
Shouldn't there be some sort of access control?
Yes, there should be a lot of things should be in the code, yeah, but it's not there, yeah. That's why these attacks exist, because of the stuff that is not present in the code. Yeah. Yeah.
Going back to the 51% attack for the L1, what kind of solutions exist? Like, I guess naively, you could limit how much value can be transferred in a single transaction, but that's destroys the use case for a lot of cases.
Yeah, so we, like with one of the projects, we were brainstorming on solutions. I don't think that there is so far at least, I have not seen a solution that is great, but at least I am aware of a solution that would prevent this attack to some degree. If you can link the exit transaction with the input transaction, if you, like, for example, if you can somehow link the exit transaction with some data from the input so that you can guarantee that, that this liquidity actually was in the pool. So that can mitigate the attack. But obviously, it's not that simple because let's say you put, I don't know, like you put $100 and then you do some trading and it's all legit and you end up with $1,000, then obviously you are quitting with much more than you put in. But it doesn't mean that it was, illegitimate. So yeah, definitely, like there is a good opportunity to think, how this problem could be solved.